You're back in the Simpkins Physics Corner. It's Mr. Simpkins. Grab your asynchronous 2 work here for this week. We are going to grind on some SHMM, or SHM, Simple Harmonic Motion. Let's jump right into it. All right, we got a length of a spring increases by this much from its relaxed length when a mass of 1.4 kilograms is hanging in equilibrium from the spring. So we got a springy boy here, and it stretches by a length of 0.072 meters. That's how you convert centimeters to meters. But you knew that because you're AP students, right? And that is when you hang a mass of 1.4 kilograms on there. So the way I've drawn this picture, this is called the relaxed spring or the relaxed length. And by putting that mass on, it's stretched out an extra amount. So when we look at spring equations, that distance x is not the length of the spring overall. It's the stretched length of the spring, or the compressed length, whichever the case may be. What's the spring constant? All right, so let's see. So here, since we're in equilibrium, that's important to note. What that means is that the forces are balanced. The force of the spring up is equal to the force of gravity down. And if you look at your handy-dandy AP equation sheet, you can find the force of the spring somewhere on here. I know what it is, and I was going to use it, but it'd be nice to reference where it is for you guys. There it is, all the way down at the bottom here. All right, look down here. Fs equals Kx. All right, so if it's in equilibrium, Fs, is equal to Fg, which means Kx is equal to Mg, and I can plug all this stuff in. So K, the stretch distance is 0.072 meters, equals the mass, 1.4 kilograms, times 9.8 meters. I should write meters per second squared, but we're trying to grind. We're trying to get a lot of these done in a little bit of time. So I'm going to pause and do math. Oh, bam! We calculate it. K is 190.6 newtons per meter. So by setting the force of the spring up equal to the force of gravity down, we are able to determine the spring constant K. And we've done this a lot in the lab. Part B, how much elastic potential is stored in the spring? US equals 1/2 Kx squared is the expression for potential energy stored in a spring. And so all you got to do is plug it in. I'm going to pause again for some math magic because I think you guys can plug in numbers to your calculator. Bam! Calculate it again. Yo, that's some weak sauce energy, 0.027 joules. Here I got all excited about this spring. All right, a different mass is suspended, and the spring length increases by 12.2 centimeters from its relaxed length to its new equilibrium position. What is the second mass? Okay, well, it's the same spring, so it's the same K. It's just that it happened to, oh man, it happened to stretch even farther. So it stretched how far? It stretched 0.122 meters in length. And since it says it stops there, we can still assume that equilibrium idea that Fg down is equal to Fs up. And so it says what's the second mass? That's the unknown thing. Fg equals mg. Fs equals k, which is still the same spring. So that doesn't change. We already calculated what the k was for this spring. Times x, which is 0.122 meters. So if you can algebra good, you can get the mass for that one. Let's see what it is. Bam! There it is. Mass is 2.37 kilograms, which makes sense. The spring stretched further, so it has more mass on it now as we compare it to that 1.4 kilograms. I'm going to do little explaining and lots of mathing, so let's keep it moving here, people. You shoot a pebble straight up with a catapult whose spring constant is 320 newtons per meter. The catapult is initially stretched by 0.2 meters. How high above the starting point does the pebble fly? So here we go. We got this guy, and we're going to go, and we're going to squish the spring down like this. How far are we going to stretch it down or squish it down? We're going to squish it down 0.2 meters. Okay, so at this point, that is where all of the energy is stored in the spring. We call that US. And then if you let it go, boing, and you throw it up into the air, all the energy up there is UG. It's all gravitational potential energy. And what we can say is the energy that was stored in the spring is converted to all energy stored as gravitational potential energy at the peak there, if you come to rest. And so we could set those two things equal to each other. US equals UG, 1/2 Kx squared, that's an X there, equals mg delta y. I'm having deja vu. I feel like I've already done this on a Simpkins Physics Corner before. Hey, man, well, can't hurt to do it a second time, right? And so the X was 0.2 meters. The M here is 51 grams. AP students can convert grams to kilograms, right, you guys? Totes can do that. 1, 2, 3 places over. And so if we convert that 0.051 kilograms there, the G is 9.8. And the Y here is how high up it goes. I don't know. That's what it's asking me to find. But everything else is there. So let's algebra good after these messages. Bam! All right. If you need to pause it and take it in for a second, that's fine. I did some intermediate steps to catch your mouth along the way. but I'm looking at 12.8 meters. Now that's impressive. All right, I guess it is a 51-gram pebble. Doesn't take a whole lot to get her going there. Next question. Keep them coming. Block is released from rest and allowed to slide down a frictionless surface into a spring. So here it goes like this. We got a block up here. There's a springy boy over here. Cool. The far end of the spring is attached to a wall as shown. There's no picture, but I just drew it for you. The initial height of the block is 0.5 meters. So I'll write that over here. Delta Y is 0.5 meters. The mass up here is 2 kilograms. There we go. And it says the spring constant K over here is 450 newtons per meter. Solid. What's the block's speed when it is at a height of 0.25 meters above the base of the... I swear I did this problem before, but I'm going to do it for you again because I love you that much. So right here, let's talk energy. Up here, it's all UG. Halfway down, there's some UG, but some of that energy, by the work done by the force of gravity, has been converted to a different type of energy. That type is kinetic. And so for part A, how fast is it going there? So let's see. Well, the initial UG, I'll call it UGI, equals UG final plus K final. And I'm defining initial and final as the 0.5 at the top and the 0.25 halfway down. So let's see. We have mg y initial equals mg y final plus 1/2 mv squared. And I'm doing this on purpose because, look, every term has an m. That means that masses cancel. Isn't that wonderful, ladies and gentlemen? That's so fun. And so all I have to do here is fill this stuff in like that. And I'm going to pause the video after I plug in some things. And we're going to algebra good to get our answer. So that gets a 9.8. That gets a 0.5. That gets a 9.8. Our final height is 0.25 because we went down the hill. Plus 1/2 v squared. All right. I'm going to algebra good with you because some people can't algebra good. So let's see how this works. So this quantity here is 2.45. All right. So what you have to do is subtract that from both sides. You got to subtract that 2.45. Again, that comes from multiplying those two things together. So 9.8 times 0.5 minus 2.45. Oh, same thing. It's 2.45. Go figure. Oh, because you came exactly halfway down. All right. All right, and so you got that. So then you got to multiply both sides by 2. So that takes us back up there. 2.45 times 2. It takes us to 4.9 equals v squared. And then to get v, you got to take the square root of both sides. So the square root of 4.9 is going to be 2.21 meters per second. Bam! Oh, I didn't mean to change the problem. Geez, PowerPoint, slow your roll. All right, so that's how fast you'd be going at that point halfway down the slide. Let's keep trucking. How far is the spring compressed? All right. Well, again, this is energy. Now, you can set the energy halfway down the ramp equal to the final energy. P.S., the final energy with no height and no speed is all U.S., or potential spring energy. But why would I make it complicated with two forms of energy when I can just set it equal to one form of energy? So what I'm going to do here for part B is I'm going to set the UG at the top equal to the US all the way at the end of the problem. Gotta love when PowerPoint's messing with you here. I can fix that right up. Check me out. I'm going to keep my annotations. You guys, if stuff starts lagging on you, you just say, yeah, keep everything, and then jump right back in. Look at that. Now we're flying. mg delta y equals 1/2 kx squared. Those are the equations you can find on your equation sheet. Let's talk UG at the top. I feel like we already found that number. Maybe we didn't. Dang it. I got to go find it. All right. I'm going to do some calculator magic on the pause, and I'll be right back. Oh, bam! Calculator magic. You might need to pause the video to take it in to check your work. All right, but here's how you plug all those numbers in, and I'm getting 0.209 meters as the compression distance. All right, the spring sends the block back to the left. How high does it rise? Duh, 0.5 meters, because it didn't say there's any friction, right? In fact, it said it's frictionless. If there's no friction, there's no work being done by an external non-conservative force. If there's no work being done by an external non-conservative force that's outside of our system, energy is conserved. All right, so that's why it's got to go back up to the same height. Next problem. Can you tell I just had my third cup of coffee? An ideal spring has a constant K. It's suspended vertically, and an object hangs from it, and it's released. What is the... Here we go. Now we're going to have some fun, ladies and gentlemen. Woo! We're going to have some fun. All right. So here we go. We got a spring. I'm going to draw 3 pictures for you here. We got a spring right here, and we got a mass of 1 kilogram. I'm going to slow down a little bit. This is new stuff here for us. What's the magnitude of the acceleration when the extension of the spring is maximum? Okay. So what that's asking is, what is the acceleration of the block? There's picture number 1. There's picture number 2, and here's picture number 3. What are these 3 pictures? Up here is when the spring is relaxed, all right? Here is when you drop it and it's moving down, but it hasn't gotten all the way down to its maximum spot yet. And here's where it's gotten all the way down to its maximum spot, all right? So it says, what's the magnitude of acceleration when the extension of the spring is maximum? Now, at some point, actually, let me think about this for a second. Yep. Right in the middle, we call this the equilibrium position. And we know that equilibrium is defined as when the forces are balanced. So when Fs up is equal to Fg down. And that happens right in the middle of your oscillating system. If you think about the lab we're doing this week with our car with 2 springs, one on either side, if we just let it go for a while, it will come back to rest. Oh, it'll be at the equilibrium position right there in the middle. And so in our picture here for the vertical scenario, right there in the middle is our equilibrium position. That's where we know the forces are balanced. Careful though, where the forces are not balanced is down here because, in fact, there's an unbalanced force of the spring pulling up, and that's the only force acting on it. Now, is gravity acting on it there still? Yeah, but it's not balanced. So I guess we got to figure this thing out. There's quite a lot of details involved here, aren't there? Let's start from the equilibrium position because that's where things are the simplest. It's when simpler times, when life was simpler. In the equilibrium position, Fs is going to be equal to Fg, right? So that means that Kx is going to be equal to Mg. And let's see if we can figure out what these numbers come out to be. The K is 25, the X is unknown, the mass is 1, well, that's convenient, and the G is 9.8. So all I got to do is divide both sides by 9.8, and this is where the problem gets unlocked. Dude, there it is. All right. So 25 divided by 9.8. All right, so hang with me here, all right? 2.55 meters. What is that number telling us? That tells us that from up, I wish I had more colors. Oh, I do. Let me go get another color. This is going to be fun. All right, that means from this point where the spring is not stretched at all to the equilibrium position, in that drop there, or in that changing of the system, the displacement to get there is 2.55 meters. In other words, if I take my mass and the spring's relaxed and I let it go and I let it bounce until it stops bouncing, it's going to come to rest at a point where the X, the displacement from the initial position is 2.55 meters. Now that's very useful information, okay? Because here's why. There's a symmetry, there's a beauty to this. Just like the side-by-side oscillator will go back and forth the same distance on either side, this vertical oscillator will travel downward that distance, x, as well. So now we start to unlock this big energy picture of everything that's happening here. Let's see if we can use this to determine the acceleration at the bottom. Let's talk about acceleration. Acceleration is a result of net forces. We've already said that, sure, you haven't turned gravity off, right? But gravity is now smaller than the force of the spring acting upwards. But think about how far the spring has been stretched now. Up here, it was stretched a distance x, because that's the equilibrium position, right? Down here, it's been stretched a distance of 2x. Oh, okay, so down here at the bottom, we'll write a sigma F equals ma expression. Oh, don't we love... You thought it was done. You thought. Fs minus Fg equals ma. All right, and so the Fs at the bottom is Kx. All right, and instead of Kx, well, I'm going to put K2x. Do you see why I did that? Okay, because the distance is twice of the x that we already solved for. You'll see when I plug it in. Just hang with me here, okay? The mass is that, and the A is the thing we're trying to solve for. So let's plug in some numbers. Maybe it'll become clear to you as we do this. 25 is K. All right, I put 2x in there just because from the time we dropped it from a spring being at a relaxed position, we traveled a distance 2x. But our x is 2.55, so I'm just going to double that. Sorry about that. So I'm going to double that, 2.55. And that's going to get me to 5.1 meters. So that's what I'm plugging in here, 5.1 meters. Why am I plugging that in? Because that's how far we dropped to get all the way to the bottom. And it says when the spring is at a maximum extension, that's all the way to the bottom, what's the acceleration? And that's equal to 1 times A. So that's actually pretty convenient because now we just solve for A. Let's see what the A is down there at the bottom. Yo, PowerPoint, stop messing with me. 25 times 5.1. Holy buckets. Don't be hanging on to that thing. You get a whiplash here. 127.5 meters per second squared. Interesting. And when I say interesting, I mean completely wrong. Because what did I do, ladies and gentlemen? I forgot to subtract FG. I feel like that might make a little bit of a difference. So I'm going to pause and clean this up, and I'll talk to you. All right, so let me wrap this up. Oh, of course, the thing gets cut off at the bottom there. All right, but the answer is like 117.7 meters per second squared. Big idea. Equilibrium position, forces are balanced. Symmetry. The displacement to the equilibrium position is equal on both sides.